Let's get started. First, thank you all for coming to today's colloquium. We're very excited to have Zvi Bern here today as our speaker. Zvi Bern is the director and actually founder of the Manny L. Baumick Institute of Theoretical Physics at UCLA. Let me tell you a little bit about Zvi and his work. Zvi did his bachelor's in mathematics and physics from MIT. He then went on to do a PhD at UC Berkeley in 1986 under the supervision of Marty Halperin. He went on to do a postdoc at the Niels Bohr Institute in Los Alamos before joining the faculty at UCLA. During this time, Zvi was one of the pioneers of a subfield of theoretical physics, basically creating the field of scattering amplitudes, which is something that I think about also. During that time, in the 90s, there was a certain way that we would compute things in quantum field theory, which was called Feynman diagrams, obviously very famous and invented by Richard Feynman. Zvi and company found new ways to use extremely fancy ideas from string theory, twisters, and quantum field theory to find new ways to calculate things that would be relevant, say, to colliders like the Large Hadron Collider. And in doing so, discovered a lot of interesting new ways to think about quantum field theory. Methods I think that I'll talk about, which include generalized unitarity, which is kind of an extension of the optical theorem that you know from quantum mechanics. New dualities between gravitational theories and the strong interactions, which I think will also appear here. He is an awardee of a number of awards, including the Sloan Foundation Fellowship from the Alfred P. Sloan Foundation. He was an Outstanding Junior Investigator Award, and in 2014 won the Sakurai Prize with David Kassauer and Lance Dixon for groundbreaking contributions to the calculation of perturbative scattering amplitudes, leading to a new, deeper understanding of QFT and new tools for studying quantum chromodynamics. Today, Zvi is going to be telling us about some recent work applying scattering amplitudes to gravitational waves, and I hope you'll join me in welcoming him.
Oh, thank you very much for that very nice introduction. So today's lecture will be about taking ideas from scattering amplitudes and applying it to the problem of gravitational wave physics. So this is work that I did with Clifford, who you, of course, know. There's Radu Roybon. There's Xiaoshen Shen, that's postdoc at UCLA. Mikhail Salon, a postdoc here, who I'm very happy to say will be faculty at UCLA. And then Mao Zheng, who's a former postdoc. So the era of gravitational wave astronomy has begun. And I can tell you, when I started thinking about it, I found out that, for an instant, the first event was brighter in gravitational waves than all the stars are in electromagnetic radiation in the visible universe. And that's pretty awesome. So I decided, yeah, this is something I should work on. So the little problem is, of course, we're particle theorists. We don't do general relativity, really. We certainly don't do classical general relativity. And how can we contribute to this problem? How can we make a difference? Well, that's what I will tell you about. So at first sight, if you look at the problem of particle physics, we think about colliders, beams of protons, and then out come particles, jets of particles can come out. And this involves unbounded trajectories. It involves ideas from gauge theory, QCD, and most certainly it's quantum field theory that's involved here. The problem of general relativity, the bounded orbits, that's different. Well, first it's bounded, and then it's classical physics. So what does this have to do with that? Well, that was understood quite a while ago. It was back in Japan. 1971, Iwasaki understood about using Feynman diagrams to extract information on the interaction, let's say, two black holes or two particles. And where does this intuition come from? Well, it's pretty simple. This is long wavelength radiation that comes out. So as far as we are concerned, these black holes are points. If these are points, then we can use the ideas of point-particle quantum field theory. So there is immediately a connection just from thinking about the hierarchy of scales here. And this was systematized by Goldberger and Rothstein, and then many other papers followed. And what I want to show you is that the ideas we have in particle physics, theoretical particle physics, they're in fact ideally suited to push state-of-the-art calculations for gravitational wave physics, even though they look like they're rather different problems. So the first point of why we think that, or we thought that we could do something, is because we have gotten very, very good at perturbation theory, gravitational perturbation theory. Okay, it's the wrong kind of perturbation theory. It's the perturbation theory that's quantum. It's for scattering amplitudes. Nevertheless, we are very good at it. So can we then figure out how to apply this? So there's two serious issues you have to worry about. Well, first it's quantum, not classical. And then this unbounded orbit problem. And the topics of this colloquium, what I'm going to explain to you is how we have gotten very good at perturbative gravity. I'll show you our secrets. Well, actually, it's not secret because I try to tell it to anybody I can find. But there's some ideas that are behind it that are pretty cool, I think. And then also, of course, dealing with this problem, how you can make the transition from quantum to classical, and also from the unbounded case to the bounded case. Well, what do we want to do? So we want to think about the basic problem for LIGO, which is the merger of two black holes after radiating, giving off gravitational waves, and there's an in-spiral, there's a merger, then there's a ring down. The part that we want to focus on is the in-spiral phase, and the reason is because we have the appropriate hammer. It's to do analytic perturbation theory is what we want to do. That's the basic technique that's used for this part. For the merger part, that's beyond perturbation theory. You need numerical relativity. And then the ring down phase, you can again use a different kind of perturbation theory. Now, I should add that the numerical relativity, of course, feeds back on this because it allows you to tune models of waveforms that you can you create based on the perturbation theory. And the reason why you need very high precision is because if you're watching the wave for a long time, then errors in the phase can accumulate. Okay? So what's this post-Newtonian approximation? I think you all know what it is just from the name. It's the next step beyond Newton, or the systematic expansion beyond Newton. So the idea is that we expand in the gravitational coupling constant, we expand in the velocity, and this is very natural because the virial theorem states that the velocity and this potential, there's a simple connection between them, same order. So you do this double expansion, and for technical reasons, it's useful to do that. What the post-Newtonian approximation is very simple. You're just expanding higher orders Newton's constant, higher orders in the momentum. You'll recognize the first term in this Hamiltonian. That's Newton. This next term, that was done by Einstein, Intveld, and Hoffman, as well as other people. And then over the years, people have systematically been computing to higher and higher order. And they don't do this because it's fun. It gets a little complicated. They do it because it's important. And you can see over the years, just this is relatively recent, all the way to the fourth post-Newtonian order, it's 2017, and then repeated using quantum field theory ideas in 2019. But probably the best way to explain that it's important is, of course, that it can be measured. So this plot, the way you should read it, is if you see a dot lower down, it means that LIGO is more sensitive. If it's higher up, it means it's less sensitive. So if you look at, let's say, the Hulse-Taylor binary pulsar, and you say, what were they sensitive to? They're very sensitive to Newton because they're watching it for many, many orbits. And then they're, of course, sensitive to the gravitational quadrupolar radiation. That's this dot over here. And you can see LIGO is, of course, sensitive to not only to that, much higher sensitivity, but it's also sensitive to all these corrections. So the simple argument why we want to do these orders of perturbation theory is because you can measure it. And not only that, probably more important, not only can you measure it, but it's a basic input into the construction of the templates that are used to extract the gravitational wave signal. Okay, so there we were thinking about working on this problem. And the question was what to work on. So there's various problems you can choose. And it turns out LIGO, for all its technical complexity, in a sense the experiment is simple. You're measuring a phase and an amplitude. So it limits what kind of questions you have to ask. It's not like the LHC, which is a much more complicated, has much more complicated physics. So we construct a list. We could think about spin. Many people were thinking about spin. Think about finite size effects. This is very important, by the way, for neutron stars. New physics effects, radiation, higher orders, and perturbation theory. So I run by a simple philosophy. If I want to spend a lot of time on something, it has to make a difference. So there's, you could say, various boundary conditions of what kind of problem to solve. It needed to be extremely difficult using standard methods. It needed to be of direct importance for LIGO theorists. And it needed also to be in a form that, at least in principle, it could enter the LIGO analysis pipeline. So it needed to be a calculation that, in principle, is directly relevant. And there's the answer. That was the one. High orders and perturbation theory. It definitely satisfies the extremely difficult part. And the one that we decided to do, it's called two-body Hamiltonian at third post-Minkowskian order. And okay, so you say, what is that? Well, Alessandro Bonanno, who's one of the theorists in the LIGO collaboration, so he laid it out for us. This is Amplitudes 2018 of what needed to be done and how to think about it. So it's a kind of messy slide, but I like it because it's a slide from Alessandro. So if we're looking at the post-Newtonian approximation, then we look down these columns. So the 0pn, that's Newton. This is this one, 1pn. If you look down this column, those are the terms from Einstein, Infeld, and Hoffman. If you see the 1 over r here, that's it has this power of g. And people have gone, here's the green, have gone to this fourth post-Newtonian order. If you look across the row here, that's what at least they call post-Minkowskian approximation. And we in particle physics, we have another name for it. We call it perturbation theory. It's just an expansion in Newton's constant. And everything else, the velocity, you just do it exactly. And this is completely natural in quantum field theory. This is the way relativistic quantum field theory is set up. So why in the world would you want to do this expansion? You'd really like to keep things, all of this together. And this is very natural from the point of view of relativistic quantum field theory. So this is just an expansion in Newton's constant. And there it is. This one had not been done. Alessandro said, go do it. Oh, and here's another paper. So this is a very nice paper that lays out the groundwork. So, by the way, the answer to the question of what's important, what's hard, it wasn't that complicated to figure it out because it was all pretty much laid out. For example, this paper really lays it out. I've never seen a paper like this that lays it out like this. It says, and we urge amplitude experts to use their novel techniques to compute the two-loop scattering amplitudes of scalar masses from which one could deduce the third post-Minkowskian effective one-body Hamiltonian. So there was an invitation. It's hard to resist an invitation with this kind of clarity. And, of course, it satisfied all the boundary conditions, so this was clearly the right problem to work on. Now, let's first think about quantum field theory and scattering amplitudes. So that's, say, a rather different-looking problem. So that would be the kind of problem that you need to make predictions at the Large Hadron Collider for the particle detectors. For entertainment, here's a Higgs boson event. And one of the key ingredients of doing this is you have to do, well, we don't do it by Feynman diagrams, but essentially Feynman diagrams to compute scattering amplitudes. And later in the talk, you're going to hear about tree diagrams, and you're going to hear loop diagrams. So the way you should think about that is loop diagrams are complicated, tree diagrams are simpler, loop diagrams are higher orders of perturbation theory. Okay. Now we have the tools. So this is our Scientific American, May 2012. I don't know if we have to do with unification, but there it is on the cover. And the key theme, if you open this up, it's all going to be about recycling. This idea that when you start a calculation, you don't want to start with a fresh piece of paper and then you just start doing a new calculation. You'd like to use information from simpler calculations. You want to recycle. You want to take simpler calculations and assemble them in an appropriate way such that you can do much more complicated calculations. And the main idea, whatever we do not want to use Lagrangians. We do not want to do Feynman diagrams. Feynman diagrams, the orders that we'll be talking about, they become problematic. Okay, so what I'll do here is I'm going to show you some of the advances. I'm not going to show you all of them, but a few key ideas, a few neat things that feed directly into the gravitational wave problem. And then there's many other advances, a long list of advances, all sorts of things related to mathematics, which I won't discuss here. So let me just show you one of the examples, and this is something that we did use in the gravitational wave computation as a way of cleaning things up. And that's the idea of using good physical states. So let's just consider a very simple problem. And this would be something that you might need if you're interested in studying what's called jet physics at the LHC. It's the 5-gluon problem. So it's 2 gluons come in, 3 gluons go out, and then they hadronize in some way. And we can open up the textbooks and just do the calculation. This is actually a small piece of what happens. You just get some giant mess. There's no structure. It looks like, well, it's just a complicated calculation. If you're wondering what this is these are dot products of momenta and polarization vectors of the gluons. Actually, it's like a 25th of the whole thing. Oh, that's not good. But in fact, the problem is that we're not organizing it the right way. We're not thinking about it the proper way. We're thinking about it in terms of these polarization tensors, polarization vectors. The way we should be thinking about it is circular polarization, or helicity. If you use helicity states, and I really mean circular polarization, I mean, it's done in some fancy way with spinners. You'll see some these are spinner inner products here. You do it in some nice way using these helicity states. Then, in fact, this page here that you see, it contains the same information as was on the other page. There's no extra new information that you can find in that mess. So clearly, this is a much better way of thinking about it. And this has to do with focusing on physical states. Now, as you go up in complexity, let's say you start doing loop diagrams, pretty soon you start paying a severe penalty, especially as the number of legs, like for example, this one doesn't look so bad. There's only 5 legs, but there's a massive particle there. The number of legs or the number of loops increases, then things spiral out of control very quickly. And a lot of this trouble has to do with violating Einstein's relation between energy and mass. So physical particles, you have an equal sign here. But according to the Feynman rules, and this is for good reason having to do with the uncertainty principle, you're supposed to integrate over all energy and momenta. So clearly, this cannot be true inside the diagram. You can use words like virtual particles, but then it's unphysical, non-gauge invariant states is what gets used. And you don't want to do that. You want to use physical quantities. It's a simple lesson. When you do a computation, you don't want the intermediate steps to be unphysical. You want, as much as possible, as you're computing, that the individual pieces have physical meaning. And that way, you get enormous technical simplification. It's a good rule of thumb. And maybe you could say, avoid the virtual particles. We don't like them. And most of all, don't violate Einstein's relation. I'm not going to go through and explain exactly how this is done, but let me just say that there's systematic rules, systematic assembly of complicated problems like this loop problem. There's a loop here. This little blob means the set of all Feynman diagrams that are in this tree diagram. But anyway, there's a loop diagram here, and there's an assembly of this loop in terms of the trees using only on-shell data. On-shell just means Einstein's relation is satisfied. Okay? And then you can do this very generally. And there's a concept called generalized unitarity, where you start putting more and more legs on shell. Every exposed line here is on shell. In fact, these same diagrams that you see here, this thing, we'll see this in the gravitational wave problem, exactly these diagrams. So there's complicated objects are built out of simpler objects. And there's a systematic way of doing this. And I should say this has been proven very useful for collider physics as you get to more and more complicated processes involving more and more particles and jets. And the problems get very hard, but using these types of ideas, you can keep it under control. And it really works. All the codes use some elements of this basic idea, the modern codes. Now let's talk about gravity, because that's really the subject of this colloquium. So the first thing, when you look at perturbation theory with gravity, you do something like this. Maybe you start with the action. You could do the equation of motion, but it'll be very similar. What you do is you take the metric, you expand it around flat space or some background. It doesn't have to be flat. And then the graviton field is the fluctuation on that background. And you can just go home and stick it in there and just see what happens. And pretty much the answer is a catastrophe. That the perturbation theory just looks terrible. And I'll show you a little more detail. Well, first you get an infinite number of interactions, contact interactions. You can have as many gravitons as you want interacting at a point. But really the deadly part is it's already here. This thing you'll see is pretty complicated. And if you compare this to what happens, let's say, in QCD, in gauge theory, non-abelian gauge theory, it's much simpler. You only have 3-point and 4-point interactions, and these are relatively simple. Actually, just to compare, let's have a comparison of the 3-gluon vertex. The 3-gluon vertex of this is now non-abelian gauge theory, what you need in QCD. You'll see there's a kinematic factor that, okay, it's a little complicated, but not so bad. And there's what we call the color factor. Non-abelian gauge theory has different charges, and these matrices, these color factors, keep track of that. And if we compare that to the 3-graviton vertex, you see this thing is much more complicated. The notation hides some of the complexity. A P6 means you have to add up 6 terms. There's like 6 permutations that you need here. The sim means that you have to symmetrize in these indices. A graviton is a symmetric tensor, so you have to take the symmetric part. You get 100 terms. And anyway, the reasonable conclusion, if you're a smart graduate student and your advisor points you to this vertex, probably the right answer is, I'll go work on something else. This is not a happy vertex. And you can do some simple counting. It's kind of amusing. You can look at high loop calculations. We're not going to talk about that. We're going to talk mostly about 2 loops. But anyway, these are the types of calculations that we are interested, at least in quantum gravity, very high loops, even 5 loops. And you can do a little counting of what the vertices mean. If you If you stick in the vertices, you stick in propagators, and you just count out how many terms you have, you get completely ridiculous numbers. 3 loops, maybe make some guess. How exactly you count, it's not, it's not precise, but never mind. Count it any way you like. It doesn't matter. It goes completely crazy. Very high loop orders. You can get numbers like this, 10 to the 31 terms. By the way, that's more terms than there are atoms in your brain, and that means you can't do the calculation because it just won't fit. And these types of problems we now do routinely. And notice I didn't say we do them easily. I said we do it routinely. And an essential problem, you could say the fundamental flaw in the mess is we're looking at it the wrong way. We're thinking about it in a way that violates the Einstein relation, the on-shellness. So if we have gravitons or gluons, we want to think about it on-shell. You use the simple relationship between energy and momentum for massless particles. And now when you do that, and also you want to use the physical state projections on the outside here, you find something really amazing. You find that Einstein gravity, when we make these particles physical, the vertex, the interaction of 3 of these particles, is given by 2 copies, the square of the gauge theory factor. You throw away the color factor, and you stick in another gauge theory factor, this kinematic factor. Now, you might say, okay, that's very nice, but so what? This is just a little piece of the thing. But in fact, this is the key. This is the essential part. Because we have technology, or a way of thinking about quantum field theory, entirely in terms of on-shell objects. Just from here, right from here, we can build to all orders of perturbation theory. We know how to build Einstein gravity, just from here, from the information that's sitting right there. And the first realization of that idea, that came from string theory. By the way, everything I'm going to say, I think if it was without string theory, we wouldn't know where we're going, and there's no way we could see the things I'm going to tell you about on how we reorganize the perturbation theory of gravity. So back in 1985, the first string revolution, there was a nice paper, this Kawai and Tai, who wrote down relationships between gauge theory amplitudes. So there's some technical thing about color ordering, but never mind that. These are just gauge theory amplitudes, and it tells us how to rewrite gravitational amplitudes in terms of gauge theory. So now, if you want to compute one of these tree amplitudes, so it's the simpler problems, the tree amplitudes, the way you do it is you do the gauge theory one, and you already have that because if you don't have it in gauge theory, there's no reason you would even think of gravity. So we already have that. And what you do is you multiply and you add, and then you're done. So that's very cool. So this tells us something really profound. It tells us gravity is derivable from gauge theory. It's essentially the same thing, and not in some vague way. It's in a precise way. There's a precise set of formulas. And we understand how to do this in general at tree level, these formulas. Okay. We'll be talking about loops later. And the thing I find actually rather remarkable about this, so now is, God, I don't want to count how old I am, but anyway, many years later, we understand this, and we understand we understand a lot about scattering amplitudes. And you go back and you go to the Lagrangian, the original Lagrangian, Einstein's Lagrangian, and you ask a simple question: why is this true? It's not obvious. There's no simple explanation of that. Yes, you can brute force it. You can prove that this is right, order by cranking away, but it's not so simple. This to derive it from the Einstein action. And the other thing is, this is a very general property. It actually does not rely on the existence of a string theory. It's something that you can see. That it holds very generally. Now, there's another way of looking at this that is actually extremely powerful for looking more generally beyond the tree-level amplitudes. It's what we call duality between color and kinematics. So it turns out that the secret of gravity perturbation theory, it's not to be found in gravity. It's to be found by understanding gauge theory. So what is this? Well, there's the vertex, the 3 vertex. It's our old friend. Now, it has these different components. There's this color factor, and there's this kinematic part. The color factor, what it does for a living, because it's based on a Lie algebra, it obeys the Jacobi identity. That if you wrote down the color factor for these diagrams, there's a relationship between them. And that's just a simple fact from the Lie algebra. So you can go home and check this for yourself, because this works no matter how you do it, as long as you do it correctly. What you want to do is first put these states on shell, and then what you want to do is absorb this 4-point interaction in these other 3 diagrams using this fancy identity. One is S over S, where S, T, and U are the Feynman propagators. So this gets absorbed in the other 3 according to the color factors. And you can go home and check this, that after that rewrite, the kinematic numerators, so these numerators, they come from here and they come from this contact term. The kinematic numerators, they satisfy exactly the same identity as the color factor, the same Jacobi identity. And there's various proofs of this, that this is true in general. I can show you, let's say, 5 points, how it works. What you do is you write the amplitude in terms of 15 diagrams, and then what you do is you identify the Jacobi identities of color, and then you enforce that these kinematic numerators satisfy that, such that you get the correct amplitude. Now it's non-trivial. If you try this at home, it's not going to work, because it is non-trivial to assign all the different pieces in the right place. Okay. Anyway, it's proven that you can always do this at tree level. So you say, oh, this is very amusing, very entertaining, but so what? What does this have to do with anything? Well, this has everything to do with gravity. So let's just do that.
Standard way to find these rearrangements?
There are now many papers that give various ways of doing it systematically. In the early days, the answer was a little brute force, but now there's algorithms for generating this, at least at tree level. A loop level is another question. So let's take an endpoint tree amplitude. We write it in this form, and we've adjusted things so that the Jacobi identities, the same identities hold for the numerators, the kinematic numerators as the color factors. And the rule is, if you want gravity, what you do is you take the color factor, you replace it with a numerator factor. So that's simple. It's like magic. By the way, there's a definition of magic. The definition is we don't have a full understanding of why this happens. We just know it's true. But the underlying reason, that's more obscure. You expect that there would be an underlying Lie algebra associated with these kinematic parts. That Lie algebra, it's only little bits and pieces are understood of it. Okay? And you get, honest to goodness, Einstein gravity just by this replacement. And clearly, this cries out for some kind of unified description of gravity together with gauge theory, presumably along the lines of gauge theory. But you see, in detail, the same kinematic factor, the same dynamics, the details of how the particles interact, it's the same. You see the same numerators. Here there's 2 copies of it. There's 1 copy. This is clearly something very profound that has not been fully understood. But of course, I'm a practical kind of guy. Well, I don't need to understand it, the underlying reason. What I need to do is know how to use it. Oop, uh-oh. And that's what we're going to do. So here's the key point. Gravity, in a precise sense, is gauge theory times gauge theory. And this is going to give us awesome calculational power. And the reason is that if we want to do a gravity calculation, which is very complicated, you rewrite it in terms of something that perhaps is also complicated, gauge theory, but it's much, much simpler. And some examples, I'm not going to explain exactly what we did here, but one of the issues that we studied using these ideas, it has to do with the question of the non-renormalizability problem of gravity theories, looking at supergravity theories, looking at very high loop orders. There's our 5 loops. Right? Something that would seem to be completely impossible. And like I'm not going to say that it was simple to do 5 loops. It's not simple to do that in QCD, I can tell you. But in any case, we do it. And the one I'll be talking about is applying these ideas to the G-cube corrections to Newton's potential. And another problem, which I'm not going to talk about, but it's a really interesting one, is you say, well, look, you can do all this stuff in perturbation theory. So there's gravitons coming in, and you rewrite it in terms of gluons. But can you do this in general for some arbitrary solution, arbitrary classical solution of general relativity? And the answer is, I don't know, but there are sure a long list of examples now. So, for example, Schwarzschild black hole, the spinning black holes, including cosmological constants, radiation, et cetera, et cetera. But there's no general understanding. I think we need some help from some smart young person to look at this problem in some different way and try to understand, say, the organizational principle for all these different examples. Now, the question of the scattering amplitudes in gravitational radiation, there's actually a small industry of people who've been working on this problem, all sorts of different aspects. The connection, the primary thing is the connection of the gravitational wave problem to scattering amplitudes. There's different approaches. There's a world line approach, various technical issues. But in a sense, you could say, what's the key issue? I mean, it's all this fancy technology and all this bragging I'm doing. It's like, oh, we have this better way of doing things. But the question, can you actually do something? Can you do something that's really hard for our friends in the gravitational wave community? So the thing we're going to be after, let me just make sure it's clear. What we want to do, and this is following standard ideas that people have been doing for 100 years, is we want to replace general relativity for this two-body problem with essentially a potential or a Hamiltonian of the type that Newton would have liked, with some corrections. And that, in a sense, what it does is that it extracts the physics juice, how the black holes interact, but it does not rely on the complexity, the formalism of general relativity. But it carries exactly the same information. And that's what we want to do. And we want to get this G cubed, this Newton's constant, so the G cubed piece, all orders in velocity, that's what we're after. How do we do it? Well, there's a very beautiful paper, Chung, Rothstein, and Salon, who explained exactly how to do this, what the methods are. So the basic idea is to take ideas from this, the effective field theory community, and then also ideas from amplitudes community, combine them in such a way that we get out these potentials. Now, at first, it looks like a kind of crazy thing to do because this is a full quantum theory. And that seems like a very poor place to be starting if you're interested in classical physics. If you're interested in classical physics, it seems reasonable to start with classical physics. But on the other hand, there's almost magical simplifications. If you're thinking about going to very high orders, not just the one we got, but really thinking beyond that, how far can you go? Let's say we want to go to 5 loops. Well, then we have this almost magical simplifications that we can take advantage of. Now, let me just amuse you with something. If you look at the lowest order, how this works, it's actually quite simple. You can find it in textbooks. Like Tony Z's textbook discusses this for the gravitational case. How to relate a scattering amplitude to a potential at tree level. And that's pretty straightforward. And you feel pretty good because Newton comes out of that and everything is fine. But when you start looking at higher orders, certainly beyond one loop, things get a little more subtle. Things get a little more confused. And my great surprise when I started thinking about this is it turns out, at least what I learned in grad school, that was Berkeley, it was completely wrong about how the classical limit works. So what they said is that each loop is an Hbar, and therefore implying that trees are classical, loops are quantum. That is not correct. Maybe here at Caltech they teach it correctly. Well, I hope they now teach it correctly. So it turns out if you do the proper scaling, if you do it properly, in fact, it scales the other way. Instead of each loop scaling as an Hbar, in fact, it scales oppositely, like 1 over Hbar, which is kind of...
Actually, way back, Mike Duff...
No, I know. Some people knew this. But anyway, the world didn't know. Certainly when I was in graduate school, I'm afraid to say when that was, but I was taught every loop is an Hbar. That is not correct. I mean, in some technical way, it's true, but it's not. It has nothing to do with the classical limit, and it's certainly true. Other people understood this. For example, Iwasaki understood it in 1970 something, and he understood that. Where this comes from is it's actually not that complicated. If you take e to the s classical divided by Hbar, and you series expand as to try to line it up with Feynman diagrams, then in fact you just get powers of 1 over Hbar. That's all it is. And this has to do with iteration pieces, things that came from lower orders. And there's all sorts of issues you have to start thinking about, cross terms between 1 over Hbar and Hbar, what's classical, what's quantum. And the way we're going to clean this up is harnessing the power of effective field theory. So this is from Clifford's paper. And the basic idea of what we want, what we're after here, we're after a potential, right? So we want there's a scattering process, it's quantum, and you want to change it to the problem of a potential. You want to think about a potential so you could think about the bound state problem. And a clean way to be thinking about this problem is in terms of effective field theory. So this is an effective field theory. Think of these A's and B's as black holes. They're particles. We can think of them as point particles, but black holes. Pretty massive particles, but still particles. There's a kinetic term that you see is relativistic. However, there's no antiparticles here. Right? We're trying to do classical physics. So if we're going to extract a potential, we better not have antiparticles around. And then there's an interaction, and the interaction is exactly the potential. So inside here would be Newton's potential, and then the corrections found by Einstein and others. And the way we figure out what this potential is we calculate in this theory, and then we calculate in the full theory. You line them up, and then from that you can deduce what this potential is. And once we have the potential, we're good to go, because that's what our friends, the LIGO theorists, what they want. So just maybe just to do this a little quickly, the way we do it is 2 calculations. One is complicated, full general relativity, and you can take out all the methods that the fancy methods for doing it. Amplitudes methods, double copy, generalized unitarity, loop integration, and then out comes a gravitational amplitude. We should, as we do this, we should be thinking about Hbar goes to 0, because we don't want to overcalculate. The quantum calculation is extremely hard if you did the full thing. It's actually just beyond the means of being able to do it using modern methods if you did the full quantum theory. So you really want to take advantage of that. And then simultaneously, you do another calculation in the effective field theory, where you build an ansatz for the potential, and then you feed it through with Feynman diagrams. This is a simpler object, so we can just use Feynman diagrams. And then you integrate. And then what you do is you match these two to then deduce what the potential is. We have the potential, we're good to go. Yeah, hold that question. So Mark is right. You do not have to do a loop integral exactly. It's just the loop diagram has the information you want. Okay, and there's two things that help you greatly connected to what you asked about, which is that one thing is we're only interested in long-range forces. So the black holes are far apart. And that means the gravitons are long range. So effectively, they are on shell. Right? If they're effectively on shell or you could say from the point of view of not wanting any contact interaction, there's definitely a Feynman propagator here. We can think of this as on shell. We're in, I don't know what to call it, unitarity heaven, because then the problem that we're thinking about has lined up with the technical means of doing it. And then we're also interested only in the classical potential, and that actually enforces a constraint connected to Mark's comment that, in fact, one more line, a matter line, is on shell, and that enforces that you just pick up a residue from the energy integral. So you're actually not doing like a full quantum loop integral, as you might have expected. Nevertheless, the loop pieces, this is a loop diagram, sense that it's built out of these trees. These blobs represent trees. And the information is contained in one of these loop diagrams. So if we want the order g square, this is the only object we have to compute. If we want the next order, then we have more of these objects to compute. And these objects are relatively simple because they're built out of simple pieces. There's a double recycling we're going to make use of. One recycling is we take the trees and we make loops, and then we take gauge theory and we make it gravity. So it's this double recycle that we use. So maybe just slightly technical, but it's just telling you how to multiply things. So suppose we're interested in doing the second order. Ultimately, we want the third order, but suppose just a little warm-up, look at the second order. The way you do it is you take 3 amplitudes of gravitons with, there's matter here, there's the black holes, and then there's gravitons. And what you do is you just multiply them. You sum over the internal states, and then you recognize that these gravity tree amplitudes can be rewritten in terms of gauge theory objects. Okay, so you get a nice formula like that. And I couldn't resist showing this to you. It's maybe a little more technical, but I just couldn't resist. So these are the building blocks. If you're interested in this problem of the order g squared term, then what are the inputs you need? And these are the basic building blocks. You take these fellows and you multiply them. We have to factorize on a pole there. But you just take these simple objects written in terms of helicity variables. That's what those inner products have to do with. These are helicity variables. So what happens is this gravitational problem kind of trivializes that it has a very simple compact structure. And then you can do a little bit of algebra and you get a nice answer that looks like this. And this is, by the way, this is for the gauge theory. This is the warm-up. So if you want to do gravity, you just take 2 copies of this. Do it twice. And that's on the next page, and you follow the same algebra. And you can see it has a very similar structure in terms of the same pieces we saw on the last slide. And that definitely is not an accident. It was built that way. Okay. And you can see there's this double copy that's visible. You see something raised to the 4th power. This thing was raised to 2 powers. Well, if you square this thing, you should expect 4th power. And, okay, I'm not going to explain in detail exactly how we did the next order, but it's the same basic idea. You take these tree amplitudes of gravity, you turn them into tree amplitudes, products of tree amplitudes of gluons, and then you multiply them sum over states, and that generates an integrand. And The worst piece you encounter is also very, very simple. It's a 5-point amplitude. It's a very compact object as well of gauge theory. You feed it through the machinery. And then something very important, which I'm not going to discuss here, is to integrate it. But it turns out their paper lays out how to do the integrals. In our long paper, we have many, many pages explaining in detail how to do all the integrals. That's something pretty important, of course, to know how to do that. And to do it in a way that does not require the full quantum calculation, because that is a very hard problem. Okay, long story short, there's the answer. So this is the scattering amplitude, but it's taken in this classical limit. So you're throwing away all the quantum pieces, just leave the parts that you're interested in. And it has a very compact structure. Now you're going to look at that and say, oh, that looks like a complicated formula. But remember, we're now at order g cubed in general relativity. Right? So the fact that the thing fits on a page is pretty remarkable. Okay, and it's in terms of some kinematic objects. And whatever this thing was, as I showed you, our general relativity friends were asking help. So they say this is not so trivial. Now the thing that our friends in general relativity want, they don't want an amplitude, because this is some hybrid thing. It's like a quantum amplitude, but only the classical pieces that contribute. It's not what you want. What you want is a Hamiltonian, a good old-fashioned Hamiltonian. Something that you can look at and you can find Newton. That's what you want. So you go through the matching, and that's what this object is. It's a good old-fashioned Hamiltonian. It's relativistic, all orders in velocity. The first term here, this is where we can find Newton. Okay, it looks a little more complicated, but that's because we're keeping all orders in velocity. Newton is static. Right? Einstein, his contribution, it's a piece of this and a piece of that. Okay, and then this is the next order. Okay. Now, one thing you might be wondering about, which of course we were, of course, wondering about, is what we did. Is it correct? But that's a kind of important. If you have a better way of doing things, it would not go well if you do it incorrectly. So we needed some very strong checks. The way to check this, the best way, is to, of course, compare to the high-order calculations that have already been done. So they were done in a different framework. PostNewtonian, you series expand in velocity, you series expand in Newton's constant. To match them, what we do is we series expand in velocity. But the little glitch is to make a comparison. You can't do it directly because they have one Hamiltonian, we have another Hamiltonian. And there's no way these Hamiltonians would line up because, remember your classical mechanics, the canonical transformations. So what you need to do is find a canonical transformation. But that's really not so hard in principle in the sense that you can brute force it. You just have to find a canonical transformation that matches two Hamiltonians. And that, it works. And there are various other checks. Actually, it's a nice paper, Bini and Damour, where they go on to the next order and they verify the overlap is that we have it correct. Oh, I couldn't resist showing you this. So this is, in fact, what we compare to. It keeps on going. So you're wondering, well, you can wonder about a few things, but one thing is, why is this thing such a mess? Now, there's two answers to that. One is it's easy to take a simple function and series expand it and make a mess out of it. And that's part of what's going on here. The other has to do with gauge choices, that there's a gauge choice that's done. This is a ADM Hamiltonian. And this thing has gauge dependence that makes it messy. Now, part of what we're interested in here, it's not just to do one or more order of perturbation theory and then maybe another order. Okay, that's something we're interested in, but really what the goal is not only to find better methods where you can really go to higher orders, but to also understand the structure of perturbation theory. And for that, you need relatively compact formulas. And this on-shell way of thinking about it is very natural for generating such expressions, because things that are garbage, gauge dependence, get thrown away automatically. Or at least automatically if you don't do things in a dumb way. Now, shortly after our paper, this was 8 days later, this was actually very nice. A simple question: what effect does this have on LIGO? Well, they didn't answer the question, and I don't know what the answer is. That requires further study, but at least what this shows is that they're very interested in this question of what kind of improvements happen if you take this new information and you feed it through various models. There's something called effective one-body interactions. And then there's tuning that has to go against the numerical relativity, and there's a whole setup that it has to feed through. I actually don't know what effect it has. They didn't answer it, but they did hear the little quote. This rather encouraging result motivates a more comprehensive study. So at least we learned that indeed they are interested. Now, I think the most exciting part of this is the methods they're far from exhausted. The hard part in all this was to figure out how to do it. The actual computer, the amount of computation, it's nothing like any kind of general relativity calculation that I've ever done. So it's clear there's much more that can be done. And we started looking at the next order. And the methods certainly look up to the task. But I think probably something more important is that, the way we did it, it was based on having a certain technology and thinking about it in a certain way. And now that we have a better understanding, it's pretty clear that there's much better ways of doing it than the way we did it. And I think, when we look 5 years from now, we look back at how we originally did it, it's going to look pretty clumsy. And there's various things to investigate. Obviously, the obvious thing, just go to higher order. But I think something much more important than just going to higher order is to really think about trying to resum in Newton's constant, not just to go after one order, but at least in certain corners of parameter space to try to get the whole thing, non-perturbative pieces. There's other things, getting radiation into this story. By the way, I should comment, the way radiation is normally done is through a separation of scales. That first you do the conservative part, and then you feed back the radiation on that. So we're actually, on dealing with that separation, we're just following the standard way of doing things. But of course, you want to study the radiation itself. Spin is something that's very popular. I think almost everybody is working on that. Finite size effects, that's something else that I think at least certain people are going to be thinking about. And I think we can expect many more advances just thinking about this way of attacking the problem. So the summary is that particle physics, it gives us new ways to think about problems of current interest in general relativity. This double copy idea, it gives us a unified framework for gravity and gauge theory. And if we combine this with the effective field theory methods, we get a powerful tool for gravitational wave physics, and we provide it in a language that is useful to theorists at LIGO Virgo. And as a first example, we obtained a state-of-the-art result, this order G cubed, Newtonian-like potential. And I mentioned just now the methods, they're nowhere close to exhausted. The higher orders in G, resummations in G, spin, finite size effects, these are all things to be thinking about. And the final summary is that we can expect many more advances in the coming years, not only for gravitational wave physics using these ideas, but more generally for understanding gravity and its relation to the other forces through this double copy. And if you're interested, there's some reading. Okay, thank you.
At the formal field theory level, there are two sort of irritating coincidences. First of all, if you use Hbar's instead of metrics, they look like Yang-Mills potentials, like E mu A.
Well, we should talk about that privately, but yeah, we should discuss that privately.
And my other point is that if you write Yang-Mills and gravity both in first order form, they're both cubic. And so, but that's of course.
The problem isn't, the problem was already at the 3-point vertex. And in a sense, what you would really like, is you take a calculation in that theory and you import it to this one. And as far as I can tell, there's nothing with Vierbeins or anything like that where you can do anything like that. So it doesn't help you in the sense, at the end what happens is something that's very messy gets replaced with something else that's different. It has some nice features like maybe no higher point, but it's still messy.
No, I was thinking obviously not that wouldn't help you at the actual calculation level, because you're already doing as well as you can here, but more to motivate some kind of understanding of the
I have tried, I have tried and failed, but maybe that's not a statement that it cannot be done.
Well, you're too old according to your criteria.
Yeah, and I've tried and failed. I mean, it seemed pretty reasonable what you're saying, but I couldn't. It gets confusing very quickly. The basic problem is that general relativity has unphysical degrees of freedom, and unless you line things up perfectly, it'll contaminate any simple correspondence. Any simplicity gets lost in the chaos of these extra degrees of freedom.
Mills has an image of that too.
Right, but at least it's simpler.
Hi. How far out of reach are the first quantum corrections?
I think we can do it if
I
we
meant
wanted to.
experimentally.
Yeah, well, no. I don't think, I don't know. It would take an act of God that somehow it feeds back into something measurable. It's,
You know how many orders of magnitude?
So this is estimated
yeah.
So it's insane. It's down by like M Planck over the mass of a black hole. It's like insanely small.
Yeah. I think we need an intervention from higher authority for something to feed back.
So you drew a lot of connections to gluons when you're doing this gauge gravity sort of duality, but can you do it for any SUN, and when do you pick which sort of gauge group to use?
Right, so there was something, yes. Oh, let's go back to an early slide. That's a good question. But there was maybe, it could be right here. So if you notice on this slide, the only thing that got used was the Jacobi identity. So SUN, any SUN, it doesn't matter. So in a sense, it's irrelevant what the gauge group is, as long as you do not use any special property of that gauge group. So if you had SU2 and you use some fact of SU2, then this would not work right. But if you're thinking just some generic gauge group, it doesn't matter which one, as long as you don't use any special properties. So it's well, a good example, you could take QCD, and you could double copy that, and it gives some gravitational theory with matter in some, in some way. It's something very general. It doesn't rely on any like specifics of, for example, the gauge group in any way. In fact, like I said, it anti-relies on it. You try using specific property of the gauge group, something's going to break on you.
But that's a deep statement in itself, that it's independent of...
Yeah. Right.
Maybe one last question.
Oh.
Well, early on, you showed that amplitude and velocity space is much simpler than
Right.
linear polarizations. Can you give any physical feeling for why that's true? As I remember, for your math lessons,
Well, yeah. Well,
velocity is invariant.
and there's a simple technical reason, if you wish. If a polarization vector, it has 4 components. So you're trying to take something with 4 components, and you're trying to squash it down into 2 components. So if you're going to do this with a 4-component object, you better have some complicated, messy projector to do that. If you're just using directly the helicity states, then life is good. You know, the theory doesn't complain.
All right, well, with that, let's thank
Thank you.